Okay, so what is the analysis of variance? We said that the true yi, so which is an observation about the population, is equal to an estimated version that we hope that they are equal, but in reality, they are not actually equal. That we have a certain error term, okay? Of course, we try our best to make these equal, or in other words, we try to minimize the amount of errors as much as possible in our model. If we rewrite this equation again by taking the mean out from both sides, it's going to be equal to yi hat minus y bar plus ui hat. If I add the summation sign from I equal 1 to n, and this is assuming that I have a set of observations that start from the first person all the way to person number n, then I can take the summation over all the set of observations, and I can also square it, equal the sum from I equal 1 to n of yi hat minus y bar squared plus the sum over all the error terms I have over the set of observations I have. This is called the analysis of variance, okay? Because I was able to decompose this equation into its version of variance. So this is the variance of the, or the difference between the population observation or the actual observation, how far it is from its mean. And this is the variance of the sample. In other words, my estimated observation, how far it is from the mean. And then also I have this part which is related, it has to be squared, to the error term. And if you still remember, we called these the sum of the squared total, and we called this one the explained sum squared, and we called this one as the sum of the squared residuals. Okay, each and every term is important because if you remember, we used it in order to, we used this decomposition in order to compute the R square, and we said the R square, it's the explanation of the model over the total variation in the model, okay? Today, we're going also to use this one in order to talk about another measure of fit, which is called the F statistic. And the F is refers to the first letter of the person who came up with this analysis of variance, and his name is Fisher. So the F stands for Fisher. Anyways, we're going to talk about different types of the F statistic. Okay, so we have different types of F statistic. Going to talk about it. So the first one is the regression F statistic. I have a special case if I have regression with only 2 regressors. Let me write this one, regression, just want to have it like consistent names. So regression with more than 2 regressors, okay? And I can also do the F test on a subset of coefficients, okay? And I can also do like we have two other F statistics. F test for one-way analysis of variance. And we have the very last one, which is the F test for two-way analysis of variance. Okay, so the one discussed in chapter 15, or the ones discussed in chapter 15, are actually these two. So these are in chapter 15, which is our reading for this week. Before I start chapter 15, I want to talk about these different types, because we were supposed to talk about them in the topic related to measures of fit, okay, with the R-square, the adjusted R-square, the root mean squared error, the standard error of the regression. So I'm going to be talking about the 1, 2, 3 first before I start the ones related to chapter 15. Okay, so the F statistic, I want you to imagine that you have, so let me call it the model or the regression model F statistic or F test, whatever. Okay, I want you to imagine that you have this regression model. So I have yi, it's estimated, is equal to beta hat naught plus beta hat 1 x1 plus beta hat 2 x2 plus beta hat 3 x3, and everything is observed over a set of observations that go from 1 to n. So everything has a sub I here because I have n equations, right? And this is the estimated model. Okay, we have learned before that I can check the statistical significance of each of these parameters separately. I discussed that we have this t statistic where it takes the gap between my estimation and my true observation for beta 1 over the standard error of beta hat 1. So we have already discussed this. So we were using this t statistic to check statistical significance, right? Now, the null hypothesis for this t statistic, and you can always repeat this to the beta 2 and the beta 3, was basically that my expectation of beta hat 1 is equal to beta 1 is equal to 0. Okay, or you can just forget about this part and you write as equal to 0, whatever you like. All right, so let me keep it. And of course, the alternative that you know is my expectation of this parameter is not equal to 0 or is equal to something. So actually, if I'm thinking that beta or x1, okay, suppose that x1 is my education and suppose that W is my wage, I'm sure that my education has a statistical significant impact on the variation of wages, right? So I'm kind of 100% sure that beta 1 is supposed to be statistically significant. In other words, I'm kind of looking to be here. So if I reject the null, I'm here. So if or in other words, the alternative is simply telling me that beta 1 is statistically significant, right? So you actually hope to reject. So if you reject the null hypothesis, then you would conclude that education has a statistical significant effect on wage or the predicted wage, right? And then you have to add this holding all other factors constant. So you have to hold everything else constant, because if this is age, if this is experience on the job market, then I want to make sure that I'm talking about just the effect of education on wage, holding constant age and experience. Okay, and I'm sure that you know that rejecting the null simply means that this T statistic that I computed from my model is exceeding the critical value, right? So you are, if it is a two-sided test, then you are in the shaded region. So you're looking for this area if I'm sure that education has a statistical significant impact. And I'm not 100% sure whether it's positive or negative, but if I'm doing like a two-sided test, but this type of relationship, you're almost sure that it's positive. So you can always just perform a one-sided positive, right? One way or one tail test. Okay, and again, you're all the time you're looking to this shaded region so that you can reject the null and conclude that your model is, I mean, like the effect of education on wages is statistically significant, holding age and experience. Okay, now suppose that I want to analyze the impact of more than one coefficient at once. Okay, so suppose that, again, I'm just gonna have like a clean slide. So again, my model is wage is equal to beta naught plus beta 1 education plus beta 2 age plus beta 3 experience, right? And it's an estimated model, so everything is with hats, like the betas with hats, and it goes over all the set of individuals I have, so I have to have a sub I everywhere I have a variable. Okay, now suppose that I want to test whether education, age, and experience have a statistical significant effect on wage. Okay, so in order to do that, I'm kind of testing more than one coefficient at once. So my test would be that the null hypothesis would be whether beta 1 is equal to beta 2 is equal to beta 3 is equal to 0. And my alternative is one of the above restrictions does not hold, right? Or you can write it as beta 1 is not equal to 0 and or beta 2 is not equal to 0 and or beta 3 is not equal to 0. And what is the idea of the alternative hypothesis is I'm allowing one of the T statistic of this coefficient to be below the critical value. So it doesn't have to be all statistically significant, but I'm allowing one of them to be statistically insignificant. And in this case, you're talking about the joint statistical significance. Okay, so the joint, because I'm talking about the combination of their statistical significance all at once. So back to our analysis of variance. How can I use this analysis of variance to talk about the model F stat? So the model F statistic is actually using, again, the explained sum squared, as is the case with the R square. So this is, again, the numerator for the F statistic, but it's dividing it by the variations coming from the error term. So this divided by this, okay? And just recall that the R square is simply this divided by this. And since you already know that the explained sum square is equal to 1 minus the total, sorry, it's not 1. The explained sum squared is equal to the sum squared total minus the SSR. So you can think of the R squared and the F statistic are very equivalent, right? So they are both using the ratios related to the analysis of variance. So let me show you here the equation of the F statistic, which is our number one, which is the model F stat. The F statistic is equal to the explained sum squared over the sum of the squared residuals, okay? However, here, I need to divide by certain degrees of freedom and I need to divide by certain degrees of freedom. So when you go here, okay, so what I'm doing here is that I'm estimating the distance between yi hat minus y bar, which is the ESS, and I'm estimating the distance between, and remember this one is simply yi minus y hat I. Okay, so I need to adjust for degrees of freedom for this component and for this component. For the explained sum squared, how many parameters you are testing, how many parameters you have in your model. Suppose I have k k x's, right? And so my degrees of freedom here would be the number of x's, k. For the sum of the squared residuals, which is yi minus yi hat, when I open this one, right, I have the set of parameters k, and I do also have one for the intercept. So I have to adjust for that. It's going to be my sample size minus k minus 1. Okay, so that's why you can think of the F statistic as an average. You're taking a certain total and you're dividing by a certain number, which is the x's, and this would be called the mean squared explained. Okay, and the next one is going to be, again, I'm taking the sum of the squared error and I'm dividing it by a certain n, right? And it's like I'm getting the average. So it's going to be the mean squared residuals. So this one is the mean squared explained, and this is the mean squared residuals. So do you get that the F statistic is a ratio between these two? And of course, if the amount of explanation is bigger than the amount or the mean of the residual term, then this is actually good, right? This means that the F is going to increase. And if the F increases, I want you to imagine that the F distribution has a certain rejection region. And this one, again, is the critical value, right? The critical value, we're going to call it F. You put here the degrees of freedom coming from the numerator, K, the degrees of freedom coming from the denominator, N minus K minus 1. So if my computed F has this characteristic, so that means my computed F would be large enough, and I hope it's large enough to exceed the critical value. So this means that if it is high enough, then you go to the rejection region. And what are you rejecting? You go back here, I'm rejecting this, right? If I'm rejecting this, then at least one of the above restrictions does not hold. So at least one of them is statistically significant. Okay, so if you reject, then you can say that education, age, and experience have a joint statistical significant impact on wage, okay, or statistical significant effect. I'm just going to correct my handwriting, it's terrible. Statistical joint, statistical significant effect or impact on wage hat, right? And which is a good result. So all of them, they are jointly statistically significant. Okay, and of course the opposite is true. Here I'm just saying it maximizes, but I'm just saying I assume that it passes the critical value. And for this part, which we call it the critical value, I want you to remember that most of the time we are working with a large sample size. Okay, so actually you can think of this critical value as fk infinity, because really I can just move this n minus k minus 1 as being a large sample as long as I can exceed the 30 observations, and most of the time we're working with more than 30 observations, so we're fine. Okay, so you can always, when you go to the F statistic table, you have degrees of freedom for the numerator, for the denominator, right? And you can actually this one is the numerator and this one is the denominator, and for the denominator you can keep going and you choose the row that has infinity sign and you check your statistical significance. Right here now I have 3 because I have 3 Ks. I'm going to go with 3 and infinity and choose the critical value so that I can compare it with the computed F. Any question? Do you have any question? Okay. Okay, so this is a simple F statistic. We have even a simpler one. Suppose that, this is number 2. So suppose that I have a model with only 2 regressors. So suppose I have, let's say, wage hat is equal to beta hat naught plus beta hat 1. What did I say? Yeah, education plus beta hat to age, and that's it. Okay, now I want to check the joint statistical significance, how important these two together. So my null hypothesis would be just for only 2, right? Whether beta hat 1 is equal to beta hat 2 is equal to 0. And the alternative is whether one of them is not statistically significant. Okay, one way to compute this is by using the t-statistic. Of course, you can use our previous method, which is the explanation of the model divided by the amount of errors in the model. You can perfectly do that, but there is an equivalent easy way of doing the statistical or the joint statistical significance. And this is coming from an equation that depends on their t-statistic. So it's actually 1/2 of the t-statistic of the first variable, which is our education variable, plus t of the second variable, which is age, minus 2 times the correlation coefficient between t-statistic of education, t-statistic of age, right, over 1 minus the estimated correlation squared of the 2 t-statistics. Okay, so this is the correlation between T1 and T2. Suppose that, like, to make our life easy and to understand this equation, let's assume I have, assume that I have this correlation is equal to 0. If you have this correlation equal to 0, I want you to imagine that this F is simply going to be equal to the average of each of the T statistic squared. That's easy, right? So this is going to be our F statistic. So in case I have a correlation that is equal to 0, then I can simply use the T statistic of education, T statistic of age, square each of them and take their average, and this is going to be our measure of the joint statistical significance. However, most of the time we have this correlation is non-zero. So we have a certain value for this correlation that is not equal to 0. So it's not equal to 0 in most of the times. So we have to adjust this equation by including the correlation term of the two T statistics. Okay. So again, if I have a model that has two x's, if I'm using this method or if I'm using this method, they are equivalent. Okay, but this method is more general because it is used when I have more than two. Okay, can be used like for any coefficient. I mean, for any model that I have more than two variables. If you just have two variables and you want to make your life easy and you have all the information of the T statistics, and if you have the assumption that the correlation or the estimated correlation between the two T statistics is equal to 0, then you just go ahead and you compute it using this simple formula. Okay. All right, and then again, you can, I'm sure that you can understand that it might be the case that this one is very small, so it's statistically insignificant. This one is large, meaning that it passes the critical value. I really don't care about one small and one large. What I care about is their average, right? Their combination, their joint statistical significance. And again, you take this number and you would be comparing it with the critical value, right? Your critical value again, and again, now I'm assuming that all the time I'm working with a large sample size. So my critical value would be how many restrictions I have. I have 1, 2, right? So it's going to be K equals to 2, or number of coefficients to be tested to, and infinity for the sample size. Okay. Next, let's go to a more complicated version of the F statistic. Suppose I have, so this is number 3, right? And you're using the F statistic for a subset of the regression model. So in other words, I have a model like this. Again, let's keep using the same model. Wage hat is equal to beta naught plus beta 1, education, beta 2, age, what else? Beta 4, let's say gender. Okay. And again, everything is estimated. Everything goes from I equal 1 to n. Okay. Now, suppose I just want to test two coefficients. I have x equal to, let me actually type it as k, because I use k as my counter for the x's. So the number of k is equal to, I have 1, 2, 3, 4. So I have 4 k's standing for 4 x's. However, what I want to test, I'm going to call it q. So this is the number of x's. This is the number of x's to be tested. Okay, so we're gonna call it q. I want to test just 2. Okay, so suppose I want to test, I might also test 3 Okay, but don't test the 4, because if you test the 4, then you're going to go back to model or test number 1. I want to, for example, I want to check the statistical significance of, let's choose any two, for example, age and experience, right? I want to check whether these two have a joint statistical significance or significant effect on wage. Okay, so in general, we call the Q is number of restrictions, because you are restricting the model, number of restrictions. In order to be able to compute that, we will need to run this regression twice. This regression, as you see it here, is called like the main model or the unrestricted model. Unrestricted model. I can have another version where I'm using these restrictions, or I'm using the restrictions I have under the null. So I'm testing age, where age has a coefficient of beta 2, and I'm testing experience, where experience has beta 3 are equal to 0. So these are my two restrictions, and the alternative is that one of the two does not hold, right? So I have to write a restricted model. In order to write a restricted model, I'm going to use this model by dropping the ones that are equal to 0. So I'm going to see which ones are equal to 0. I'm going to rewrite the model, re-estimate the model. I'm going to have a certain intercept, okay? And I'm going to have beta hat 1 education, it's not restricted, and I'm going to have beta hat 4 gender. Okay, so you have already removed beta 2 and beta 3 because they are restricted. We call this one restricted model. Now, I take the measures of fit here. So I need to look at my R square here, and I need to look at my R square here. Or equivalently, as I mentioned at the beginning, I can also, instead of looking at R square, I can look at the sum of the squared residual here versus the sum of the squared residuals here. They are equivalent because, again, go back to our very first slide. The R square is the ESS over TSS, but I can also use the SSR, right? Because I can open this one. Let me write it here. I can open the R square and say, okay, the R square has another equivalent way of, we can always write it as 1 minus SSR over TSS. Okay, so again, this is still the R square. So I can use the measure of fit based on the R square, or I can use it based on the SSR. Both are equivalent. So that brings us here. I can use R square or SSR. These measures of fit are the unrestricted measures of fit, and these are called the restricted measures of fit. And this brings us to the formula. So we have a formula for the F statistic when I'm doing my test on a subset of coefficients. It's equal to the sum of the squared residuals of the restricted model minus the sum of the squared residuals of the unrestricted model, and it's divided by how many coefficients to be restricted, Q, over the sum of the squared residuals of the unrestricted model divided by its unrestricted, right? So it's actually your main model, n minus k minus 1, and again, it has an F distribution with Q, you can call it Q infinity, right? Q infinity degrees of freedom, assuming that I have a sample size that is equal to 30 or more. So it's a large sample. And if I have a large sample, I can use the law of large numbers, and I can approximate this distribution. Okay, there is also an equivalent way. If I want to write it in terms of the R square, and this is for some reason it's more famous, where people use the one that has the R square in the formula. So it's R square unrestricted minus the R square restricted. Okay, and it's divided by Q again over the 1 minus R square unrestricted over, again, same, N minus K minus 1. It's equivalent, right? So FQ infinity. Okay, if you don't have a large sample, then this part is going to be like N minus K minus 1, which is the same here. Okay, let me give you an example, because I know it's relatively like it has so many parts to it. So let me give you this example. Okay, suppose that I have this model, which is, I'm analyzing the factors affecting the demand for college. Okay, so this is my dependent variable, and it's an estimated model with an intercept of 370 minus 1.1. The cost of college, of course, the higher the cost, the lower is the demand for the college, and it has a standard error. It's always right under it within between round brackets. This is the standard error, minus 1.5. Distance to college, of course, the higher the distance to college, the less demand. Okay, plus 0.97 rank of college, and the higher the rank, the higher the, actually this one is supposed to be negative, and you understand the idea. So I have colleges that are ranked from 1 to, let's say, up to 100, right? This one are the best, and this is, let's say, out of 100, this is the worst. So the higher the rank, right? As I go from 1 to 100, which means the worse is the college, then I would expect the demand to decrease. So the higher the rank, or as the rank goes from 1 to 100, the demand decreases. So that's why this one is negative here. Okay, and then we have the standard error. We don't need actually the standard error now, but I just, for to be complete, I have it here. Now I have an R square for this model, which is 0.468. So you have estimated this model, and you got the intercept beta 0, partial slope for the cost, partial slope for the distance, partial slope for the rank. And next, what you need to do is to see, let's say you want to find out whether, if I restrict this model by testing whether I need to remove the beta of cost. So I'm gonna call it beta cost instead of calling it beta 1, just for simplicity. And then beta hat rank are equal to 0. So I'm testing whether I can remove actually cost and rank from this regression. Are they statistically insignificant, right? So if I fail to reject, then they are statistically insignificant. So I need to perform a test. And the alternative is, again, one of the above does not hold. So this one is not equal to 0. So the restricted, you're going to use this to write the restricted model. You know that this R square is called the unrestricted because it's coming from the unrestricted model. Now I'm going to regress a model that is restricted, that has this part is 0. So this part is gone. This part is 0, so it's gone. So it's only the demand for college, right, regressed on distance. And if you ask me where did I get these numbers from, these are actually, I got them from Stata. So I have the data for the demand for college, I have regressed the data set, and I got these numbers. So these numbers are based on Stata output. And I get the R square of this model 0.442. So this one is called the restricted R square because it's coming from the restricted model. Now let's plug in all these information into the F and conclude whether I can assume that these are insignificant or not. So the F statistic is using the unrestricted R square minus the restricted R square. How many restrictions I have? So I have to divide this by Q. I have only 2 restrictions, divided by 1 minus the unrestricted, divided by, if you want to type infinity, it's going to be infinity like theoretically, but here it's going to be like, I have sample size, I should have told you it's 500 colleges, minus we have the 3k, which is the k, minus 1. So this is the number of x's in the original model, and this is the intercept of the original model, okay? So what you get is 0.013 over 0.00107, and you get an F statistic of 12.1. How can you make any sense out of this number? So you actually need to, so this one, we call it the F statistic, which is the calculated F, okay? I need to go to the table and I need to look for, or you can call it the tabulated F statistic or the critical value. So let's say you need the tabulated F for F under 2 restrictions, large sample size, and you will find it as 4.61 for the 1%. You will find it as 3.00 for the 5%, and you will find it as 2.3 for the 1%. Okay, let me remove the brackets because I'm sure that you might think this is a multiplication, and I'm like, I just want to make myself clear. So this is 4.61 for the 1% significance level, 3.00 for the 5% significance level. So this number is just exceeding the 4, right? It's exceeding all. So what you can do is simply, you're going to conclude that, let me just put this here. You're going to have something like this. This is the, let's use any one of them. Which one you use? Let's use the 1% because it's the highest, okay? So 4.61, this is my critical value. The 12.1 is here, let's say. So the 12.1 is greater than the critical value of 4.61. You conclude that, again, you reject null, and your conclusion is cost and rank are jointly statistically significant, okay? And then if I have a question about, do you think should I keep them in the model or remove them in the model, then if I have them as statistically significant, then I need to keep in the model because they do have a statistical significant joint effect on the demand for college, holding distance constant, right? And remember that holding you must hold any other factor constant, so holding distance constant. Okay, so this is our F statistic that is coming from a subset of of regressors, like a subset of the model. I have the whole model that had 3 regressors. I just wanted to test for a subset of this model. Okay. All right. So before I move on to the next types of the F statistic, because the next types are even more challenging, I'm gonna stop here, and I want you to, or I want to give you the option to redo the practice number 8. So you can go to Stata, and your password is P8. Okay, so you go to Stata, do do practice 8. If you wanna like improve your grade, I gave you like a second chance, and especially the last 3 questions if you wanna redo them. And I'll give you like what, 10 minutes, okay, and then we're gonna start again. So now it's 1:23. I'll be back at 1:33. So you were supposed to submit the quiz by that time. Okay, let me see. I don't think we can see. What do you mean the core of? You cannot see the grade? Okay, what you can do is you can take it anyways, and I'm going to take the highest grade, okay? Because I don't want to change the setting right now. So you can just take it, and then my settings are going to be choosing the highest grade, okay? Because I noticed like the last couple of questions were related to the topic that we discussed last week. So maybe it would be better to redo it, okay? All right, so it's 1:24 now. I'll be back at 1:35. I'm going to give you the time to redo practice 8, and then we're going to continue with the other types of the F statistic. All right, everyone, are you done? Are you done? No, Dan, you were late to go in. I don't know. I said we're gonna start like probably 10 minutes, more than 12 minutes ago, and you started late. What about the others? Done? You can either type or open your mic. Okay, so part is done. What about Muhammad? Are you done? Not yet, okay. All right, let's wait for, okay, let me give you 3 minutes for Muhammad and Dan to finish and submit, okay? So 3 minutes from now, and I'm gonna start. All right, so let's start. Okay, so our current chapter, which is chapter 15, is covering two other types of F statistic. So the fourth type is called one-way analysis of variance. So ANOVA, which is analysis of variance, okay, and it uses the F statistic. And the idea is, and sometimes you can call it also one factor ANOVA, okay. And the idea is, suppose I have, let's say, a sample of students, and those are 21 students. And those 21 students are divided into 7 freshmen and 7 sophomore and 7 junior. Okay, so I have 3 groups of 7s. Okay, and the idea is I'm looking for, or I'm looking to answer this question: is there a statistical significant difference in the final exam score? Okay, so I give everyone a final exam score, okay, between groups. Okay, so how many groups I have? I have 21 students and I have 3 groups. Okay, and my question is about the final exam, right? So my intention is to look at the variation in the final exam that depends on what level of schooling, or what's the level in college for each and every student. Is there any significant difference in the average of this group versus the average of this group versus the average of this group? So it's like you're getting 3 averages, right, here. So our sample, as I said, we always call the sample N, okay, and let's say our groups are K. So here I have K is 3, right? So which is the number of groups. Now, the idea of the F statistic is, again, it's an analysis of variance. So you're going to be talking about the sum of the square, right, between groups over the sum of squared within groups. Okay, and this is divided by how many groups I have, minus 1. And this one is divided by the whole sample size minus K. All right, so again, you can, anytime I have the sum and divided by a certain number, I can always consider it as the mean. So this one is going to be like the mean square between groups versus the mean square within groups. Okay, so I have the final exam, right? So you give them a final exam, and you have group 1, group 2, group 3, where group 1 is the freshman, group 2 is the sophomore group, and this is the group of the juniors, right? And then I have 1, 2, 3, 4, 5, 6, 7 students per group, right? So it's going like 7 per group, okay? My question is, or our intention is there a statistical significant difference between this one versus this one versus this one? Okay, so it's like you're getting an average for this group, another average for this group, and another average for this group. Oh my God. Okay, so, and you want to have like, this is X bar for the freshman, X bar for the sophomore, X bar for the junior. Is there a statistical significant difference between the three X means? So the between one, which is the one here, is the between groups, right? X bar F, X bar S, X bar J. What about the within groups? It's like inside each group, the variations of points, right, for each group from its own average, and the variation of points here from its own average, and the variation of points here from its own average, and then you're adding them up. Okay, so let me show you this in your slides. So I'm going to come back to here. Just want to show you in the slides. Okay, so you have all the details here. Okay, so here, let's see. When you look at, for example, I have three groups, A, B, and C. A, B, and C. And I'm talking about different types of cars, their consumption of miles per gallon. As you can see here, I have small variation around the sample means. Like here, they have a certain sample mean, right? They're kind of close together, okay? Compared to the variation among the sample means. So variation here is bigger as compared to variation within. Here, what you can see here is there is a large variation around the sample means. This one, there is a large variation around the center. There is a large variation around the center. There is a large variation around the center. However, when you compare them, they are not that far away from each other. Okay, so there is this idea of within and between. So the one-way analysis uses this F statistic and is based on certain assumptions. I have the population is normally distributed with equal variance and the sample are randomly and independently drawn. Okay, again, your null hypothesis is the same, but in a different context. So now I'm comparing sample means. So these are the population means, and I'm saying that I assume that the population or the mean of this group of students, freshmen, is equal to the mean of sophomore, is equal to the mean of junior. Here, they are not equal. There is a statistical significant variation between the groups. Okay, this is a graphical representation when of the null hypothesis. When I say that the means are equal, then they are all kind of centered around the same center or the same mean. I might have slight variations in their variance, but they are tightly around the same mean. Okay, however, when I talk about the alternative hypothesis, not all of the mu's are the same. It could be like this: I have two are exactly the same, one is different, or the three of them are different. So the F statistic allows for the fact that at least one is not equal to 0. Okay, so when we write here they are all equal to 0, here we write they are not equal to 0, or you can write at least one is not equal to 0. Okay, so again, this is a representation of the variability, and now let's talk about the within and the group. Okay, so this is the total variation that I have in the model. I can divide it into variations inside each group. So what about the variation inside the freshman group? What about the variation of the dots from the mean of the sophomore group? What is the variation of points around the mean of the junior group? Okay, or I might care about the mean of the three groups. So I'm talking about between groups. So I just have three numbers to compare, right? The mean of group 1, mean of group 2, mean of group 3. So it can divide the total variation of in your model into two parts: a part that is coming from variations within the groups and variations between groups. Okay, so how can I compute that? Of course, if I'm talking about variations of within groups and between groups, then I have to sum up over all the groups, over all the set of observations I have. So K here stands for the number of groups, whether it's the levels or treatments, and then N stands for the number of observations in group. So I said in the example I gave you, I said I have 21 students, and I said I have I have 3 groups, right? So I have freshmen, I had like sophomore group, and I had the junior group. So K here stands for how many groups you have, and N stands for the total number of observations. And this is like the observation per each group. For example, this is like student number 1, and this student is, for example, freshman. Okay, so this would be like the jth observation from group I. Okay, so this is like the final exam score for this student coming from the freshman group. And then this is the overall mean. So this is the mean of the freshman, and the mean combined with the mean of the sophomore, combined with the mean of the junior. So I have like one mean for the whole 21 observations. I like this slide because it's kind of showing us in a nice way what is the total variations. Total variations is I take each X in the model and I see how far it is from the overall mean, right? So this is the overall mean, and this is the overall mean, right? The overall sample mean, which is the mean of the 21 students I have, for example. And I take each one and I see how far it is from the overall mean, and I do square it up. So I go over all the 21 students and I compare the variations of each final exam score from the big mean, right? Which is the sample mean, the overall mean. When you think about, okay, let's think about it in terms of within. So in terms of within, it makes sense that I take, let's say, I'm going to repeat this. If I have 3 groups, I'm going to do it 3 times for each group. I want to know what is the, let's say I'm doing it for the first group, which is the freshman. I'm taking the first student in the freshman group and how far he or she is from the mean of freshmen. Okay, and then I'm going to repeat the same thing for the second student, the freshman, and then how far from the mean of the freshman, and then third student, how far from the mean of the freshman, and so on. And you keep going, and then you're going to repeat it for all groups. So let's say in my example, I had 3 groups. So starting from I equal 1 to 3 for the 3 groups, and starting for student number 1 to 21. So it's going to be like from I equal 1 to 3 groups, and over also the J, which is student number 1 to student number 21. So you're taking all observations and you're analyzing the variations within. The next, and this is when you look at the computation, what you're doing is the variations within, how far I am from the population mean of each group. So the mean squared within, and this is I needed in order to compute the F statistic. It's the sum squared within. Sum squared within is each, as I said, each group for each student, how far the final exam of the student from this, the sample mean of the freshman group. And then I need to divide it by how many I have. Or in other words, I need to get an average. So N here, because I do have N students, right? But I'm estimating K X bars. So I have K X bars. I have X bar 1, X bar 2, X bar 3, if I'm talking about my 3 groups. So K here would be 3. And then N stands for my sample, so it's going to be like 21 minus 3 in the example I gave you. Okay, so you would adjust for degrees of freedom. And as you might expect, if the sample is huge, like if I have 1,000 people, it really doesn't matter whether it's 1,000 or 1,000 minus 3, right? It doesn't make like a big difference. If you divide SSW by 1,000 versus if you divide SSW by 997, it doesn't make a big difference, right? But you would definitely need to adjust for degrees of freedom if you're working with a small sample size. Next, this is again a nice representation of the within group. Like you're taking each student how far from the mean of the group, right? And it looks like this. So this is my group for the freshman. This is my group for the sophomore, and this is for the junior. Each one has a certain average for their final exam score, right? And I'm taking each person in the freshman group how far from their own average, right? And then after I do so, I add them together. So when you add them together, you get the SS within. Okay, so the SS within, which is this one, you're summing everything that you got, all the variations that you got over students, over groups. Next, SSG. I always call this SSG as sum square between, because like it doesn't matter, but just if you see me writing it as between, it's actually like between groups. Here they call it SSG, but I write it SSB. It doesn't matter, it's the same. Okay, so what about the SSG? Now, I have only 3 groups in my example, right? So I'm going to sum the variations from, I have only 3 X bars. I have X bar for the freshmen, I have X bar for the sophomores, and I have X bar for the junior. Okay, so I'm going to take each X bar, how far from the overall mean of the observations. Okay, so you would have basically, in my example, we would have like 3 of these brackets. And here it's divided by the sample size, and the sample size in the example I gave you, I have 7 students per group, which is the sample size from group I. So I said I have 7 per group. Okay, so what you're gonna do here is gonna be like 7, and then you take like a group mean 1 minus the overall mean, and so on. And this would give us the sum of the square between groups. Okay, the X double bar here, it's the mean of overall observations, or you can call it the grand mean, or the mean, like overall mean, whatever. Now, this is just a graphical representation of what do we mean by between groups, right? SSG or SS, I like to write it as SSB, but doesn't matter. So I do have, let's say, 2 groups, and I want to know what are the variations due to the differences between groups. Okay, is there a statistical significant difference between the average score between the freshmen, juniors, and sophomores? Is there a statistical significant difference? This is what the between variation is trying to measure. Now, you have the SSG, which is computed as here. And as I said, if I have 3 groups, then I have only 3 brackets of these. Then I divide it by my sample size. Now is going to be only the groups, right? Because I'm working with averages. So I have 3 minus 1. It's going to be like K minus 1. Okay, and then you get the mean squared groups, or mean square between, it's the same. Now, what you need to do next is, or again, like the between variation is like this. I'm going to take each, as I said, I'm only working with means, right? I'm not working with the whole dots that you see here. I'm just working with the means. Whenever I talk about between groups, then I kind of summarize each group in one number, right? So you have only one number, which is their X bar. Okay, so you take each X bar, how far from the overall mean, each X bar, how far from the overall mean, and you keep going until the very last one. Again, if I only have 3, then I'm going to have 3 groups, then I'll have 3 brackets. Okay, now, after you're done, you have the mean squared total variation in the model that is coming from the sum of the squared total, and it's divided by its own degrees of freedom. This sum squared total variation in the model is divided into some variation coming from within, some variations are coming from groups. Okay, and each one, as I said in the previous slides, is divided by its own degrees of freedom. So if this sum of the squared total is divided into within and between groups, then I might be interested in knowing which one is bigger. Is the variation within each group, like within the freshman, within the sophomore, within the junior, is more important, or is the variation of the score between the groups is more important? So in order to do that, we need to compute the F statistic, and I gave you already this formula. This formula is trying to answer the question, which one is more important? Is it the variation between groups or the variations within groups? And the mean squared G and the mean squared W they are computed right here, and this one divided by this one, you get this one, same, you get this one, and so on. And of course, as I said, the total variation is coming from groups and coming from within. Okay, so this is the summary. Okay, I want you to understand that if this is your null hypothesis, whether there is, or whether the means of the different groups, right, of the different groups are the same, or at least two population means are different. So you're talking about whether the mean square groups divided by the mean squared within are the same, or which one is bigger, or there is one like is more important. I want you to imagine that if the mean squared between groups, right, is bigger than the mean squared within, of course, this means that the F statistic would increase because the numerator is bigger than the denominator. And this would give you, like, or hopefully, if it exceeds the critical value, then you would reject the null. And if you reject the null, then you would say that there is a statistical significant difference between the mean of the different groups, right? So you would say, like, this one is bigger than this one, then this means that there is a statistical significant variation in the means between groups. In other words, if I have my freshman group, my sophomore and the junior, and I have 7 of those, and 7 students here and 7 students here, which one matters more? Is moving this way matters more, and this would bring me to this one, or moving, right, vertically matters more, which would give me to this one. And the null hypothesis is about moving horizontally. Is there a statistical significant difference between groups? Okay, and if this one is bigger, then I'm going to reject that the mean of, so this is like the mean of the first group is equal to the mean of the final exam for the second group is equal to the mean of the final exam. So I'm going to reject this and accept that there is a statistical significant difference in the mean between the different groups, or the 3 groups I have. Is this clear? So is this clear? Okay, so if you have any questions, just let me know. Okay, so in terms of the interpretation of the F statistic, is exactly the same, nothing different than the one we did before. So again, F statistic is the ratio between, within. We actually care about the between, and this is based on the null hypothesis. The ratio must always be positive, right? It's sum of the squared, so it's always positive, right? And the decision rule is to reject the null if my computed F exceeds the critical value. So this is the rejection region, and you know this already, okay? This is an example. And this is an example on the one factor. Why we're saying one factor? I'm talking about the variations in the scores between 3 students, right? We have only 3 groups. So how the final exam is affected by the different groups of students. So I have just one factor, which is basically the education level, right? How many years of schooling. So whether freshmen, they just entered the school, whether 2 years or whether more. So here what we have is, again, we have 3 different golf clubs. And so we want to see if the 3 different golf clubs yield different distances. We selected 5 measurements. Okay, so you selected 5 measurements and from trials on automated driving machine of each club, and we're using 5% significance level. And this is the question: is there a difference in means in distance between the 3 clubs? Okay, so I'm kind of testing or moving this way, right? It's the null hypothesis is testing horizontally. So I just want you to notice that this table, like this number is like, they should have a longer table. Okay, so just not to get confused, these numbers are not a total or something. So we have 1, 2, 3, 4, 5 measurements from each group. Okay, so what we need to do now is, the number one thing is I need to compute an average for each club. And this is what we call the within. So we get each club and we have an average for it, right? So this is the first group, or this is club 1, club 2, club 3, and the X double bar is the overall mean, which is the mean of the 3 clubs and 5 different treatments. Okay, so we have kind of 4 means for each group, and then the overall, the big one. Next, we want to compute all the components of an F statistic. So just to remind you, you go back here. What do I need? I need everything on this table. I need to compute everything on this table so that I'm able to compute the F statistic and make an analysis out of this F, or make an interpretation out of this F. Okay, so we compute everything. So the first one is the sum squared between groups, okay? And then the sum squared within groups. And you basically follow the same formula that we have. So let's say for the first one, you're going to take, like, I have n per group is 5, right? And then you take the distance between x bar 1, how far it is from the overall mean, each group how far from the overall mean, right? And then, so this is between groups. And as I told you, if I have only 3 groups, then I have only 3 brackets. Next, for the within, what you need to do is to take each observation, it's within, right? How far from its own mean. So 254 from its own mean, 263 from its own mean, and you keep going until the very last one from its own mean. So 204, which is this number that is hidden right here, 204 from its own mean. Okay, and this is how you get the within. So within is kind of a long formula because I have to go through each and every observation I have. And after you're done, you divide by the degrees of freedom as you have it in the formula, and then you were able to get a calculated F statistic of 25.27 or approximately 0.28. Next, what I need to do with this number is to go to the T statistic, the F statistic, I should say, in order to get your critical value, how many degrees of freedom I have. So you have degrees of freedom. You need to look at the degrees of freedom of the numerator. I do have 2. Degrees of freedom of the denominator, we do have 12. And then you have the 5% significance level. You check the table and you get 3.89. Just notice that in this question, we do have a very small sample, so we didn't do like the infinity approximation. So you can just take the numbers as you see it from the table, not from the infinity row. And then you see that this 25 is somewhere in the tail of this distribution, right? So there is evidence that at least one of the population means per club differs from the rest. So they are not all the same, right? So there is a statistical significant difference in the mean, right, from of one of the groups from the rest. Okay. This is if you wanna learn how to do it in Excel, but I'm gonna show you how to do it in Stata. Okay. All right. So let's move to Stata, and I'm going before discussing the second one, or actually I'm going to discuss the second one first, because, and then I'm going to open this data all at once. All right. So the next one, I'm going to kind of skip this part. I want to go to the two-way ANOVA, so you can skip this. Okay, here. Now I'm adding another variable, right? So let me explain it here first. Suppose that, so this is two-way analysis of variance. Suppose that you want to include additional factors, right? So it's not only about the division of students between freshman, sophomore, and junior that might affect the average exam grade, but I might also need to think maybe this differs from the fall versus the spring semester, where the spring semester students are about to graduate, maybe they are nervous, maybe the fall semester they are working harder, something like that, I don't know, but I need to expand my analysis to include an additional factor. And if this is the case, then we perform the two-way analysis of variance, and the two-way analysis of variance allow us to add additional factor. Okay, and this is always used if you suspect that a second factor could exert an important influence on the outcome of your research or experiment. So suppose that, for example, I'm just giving you, okay, so let me just add here that what we need to do is we need to adding a second factor, right? That could have an important effect or influence on the outcome or the results, right, of the research. Okay, so you're adding a second factor that could exert an important influence on the outcome of the results. So one of the examples is, suppose you're doing like it's an agriculture experiment, and this agriculture experiment you want to test the yield of corn. Okay, so you have on the, it's not the differences, because we're talking about analysis, right? So it's all differences in yield of corn. This is corn using different or let's say using maybe 4 different, I'm just trying to, 4 different varieties of corn. We have different varieties of corn and 3 different fertilizers. Okay, so I wanted to imagine it like this way. I do have different varieties of corn. So this is the variety. And this variety, we can have it like A, B, C, and D. And I do have also fertilizers. And the fertilizer is 1, 2, and 3. And my outcome, the outcome I'm looking for is the yield of corn, right? So this is the outcome of this experiment, which is the yield. Like this is the measure of productivity in this example. So yield of corn. Okay, so I wanted to think about it this way. Using variety A with fertilizer 1, I'm going to get a certain yield of corn here. Okay, certain amount. Using fertilizer 1 with B, I'm going to get a different yield. With C, different yield. With D, and so on. So I can come with different combinations here because I do have 4 and 3. So I do have 3 times 4, 12 different combinations out of my model. If I'm using one-way analysis of variance, I can use one of these factors, right? So maybe I'm using how the 3 fertilizers are affecting the yield of corn. Or I might be using how the different varieties of corn are affecting the yield of corn. Now I'm kind of want to do this mix, how the fertilizers and variety are affecting the yield of corn. Okay, so you can think of it this way. So I want you to notice that here in this example, I have 4 groups. And those 3, which is, let's say this is our additional factor that we have included, we call it blocks. Okay, so you have groups and you have blocks. So we have 3 blocks and 4 groups. Okay, now one other example, I can also give you another example. Let's see, so that you can understand the idea. So suppose that you have different car types, and one of them is alpha, the other type is beta, the third type is gamma, and then you want to analyze how those different car types are affecting. Okay, so this is drivers. So the driver from class 1, class 2, class 3, class 4, class 5, class 6. And you want to see, so you're going to be having different combinations here, right? Each intersection is going to be a certain value, which is a car type versus the, right, the driver class. So this is the driver class. So I have drivers that are set into 6 different levels, 6 different classes, and I want to see, right, let's say they're doing a certain race and I want to see their speed per hour. So I can have my outcome would be the speed per hour in a certain test, for example, a driving test. It's not a regular driving test. Let's say it's a race test, and I want to see their driving speed per hour. So you have here, what you have here is, again, 3 groups. So these are 3 groups, and I have 6 blocks. And again, you want to see, is there a statistical significant difference moving this way versus moving this way? Or I might also consider some interaction or multiplication, as I'm going to show you. All right. So when you look at this example or the other example, doesn't matter, you know that we have groups and we have blocks. In other words, groups, if I'm moving horizontally, and I have blocks if I'm moving vertically. Okay, now the F statistic with this type of analysis would be comparing which one is more important to us. Is the variety of the corn matters more to the yield of corn, or the changing the fertilizer is what matters more to the yield of corn? Okay, or is it the combination between the two? Is the variety, specific variety with a specific fertilizer, is the best? Okay, so I want you to think about it. If you want to think about it in terms of a function, then it would be like this: how the yield is affected by variety of corn, and this is like the yield of corn versus the fertilizers. These are the two factors that we are analyzing here. However, the ANOVA allow us, or the two-way ANOVA allow us for a third factor, which is an interaction term, which is a variety times fertilizer, and we want to see whether this would be the best, because here I'm analyzing this effect holding this one constant, right? Next, I'm going to be analyzing the second one holding this one constant, right? And then next, I can actually analyze them both, right? So I can see the simultaneous effect of a specific variety on corn with the use of a specific fertilizer. Okay, so out of this, we can come with different types of F. I can have an F for, or let me call it, I have to call it certain name because we have different Fs. So I have an F for between groups. Okay, so it's measured as the mean squared. I told you that I write it MSB, but let me keep the notation of your textbook, MS between groups, over how far is this variation, or what is the ratio of this variation between groups from the mean squared errors in the model. And the idea of this F statistic is, or the null hypothesis, or what is this F is testing, is the K population mean is the same, right? So this is like a summary of what the null hypothesis is testing. And the K here stands for groups. And when I go back here, I have 4 groups. So this first one is moving between the groups A, B, and C, right? So what we had is 4 in the previous example. I have a different F that moves vertically. So F for the blocks. And this F is the mean squared of these like blocks over the mean squared error. And the null hypothesis for this one is the H population block are the same. Okay, so they are simply, they are actually the same, are the same, or have, it's not the same, let me just make it them, have the same mean. Okay, so you're trying to test this. And also there is a third one if I'm allowing for interaction. So the F for interaction, and I'm going to show you all the details in on the slides. The F for interaction between groups and blocks is equal to the mean square of the interaction over the, sorry, this is the mean squared error. Okay, So let's go back to the slides, and I'm going to show it to you here. So okay, so we have here, we're examining two factors of interest, and we might also be interested in the interaction between different levels. As I told you, like a multiplication, basically it's a multiplication. Again, the assumptions are nothing's different. So population normally distributed, you have equal variance, independent random samples, so nothing's new. Now, as I gave you the simple example, so you can be moving, right, horizontally between the K groups or moving vertically for the blocks. The groups are counted by K, the blocks are counted by H. And that, like, whatever you see here are all the set of observations you have. So we start with the first one, and the most challenging thing here is the number of notations that you will see. So Xij denote the observation of the ith group J block. So you go here, this is group 2, block 2, group K, group K, block 2, okay? And of course, the last one is the group K and the very last block H. Next, if I have K groups, H block, then the total number of observations makes sense, right? So you multiply K times H, you get the total number of observations. The grand mean again, or the overall mean again, is X double bar. And then if I'm talking about the group sample mean, because I do have a group sample mean and I do have a block sample means. So to make sure that you understand, so let me go back here. So if I'm computing, let's say if I am computing, this is the mean of group 1. So I'm going to add all these up, right? And divide them by the total number. Same here, this is the mean of group 2. This is the mean of group K, okay? So we do have K of these, right? That's why the I goes from 1, 2, and 3, and 4 all the way up to K, because I do have K groups. And then if I want to compute the other one, which is by block, so the by block, I need to have a certain average for each block. So I'm going to have, this is block 1. What is the average of block 1? I'm going to take all these and divide them by the total number K. Okay, and same thing. What is the average of block 2? So I'm going to take this average and divide them by K. And then same thing. What is the average of this group, and so on. So we have the block sample means, okay? And I'm going to have H of these because I do have H rows. Next, our sum squared total now is divided into, we used to have it only by groups variations, right? And then now we have it between blocks or between groups, right? And then we have the explained or unexplained, which is the amount of errors, right? Which we call it unexplained. These two are explained because they are coming from my estimation. I do have some measures from them because I do have the sample, but I always have a certain number that is coming from the error term, and we call it the unexplained. You can call this explain, explain, unexplained. So how can I compute the F statistic now? So I do have different sets of sum squares. So we have the first one is the total, but we're dividing it into between groups and then between blocks. Okay, and so you're taking, for example, here, each group average, how far it is from the grand mean. Here, each block average, how far it is from the, right, the overall mean. And this one is each sample, sorry, it's each observation I have. If I have like 100 observations, then I'm gonna have 100 of these. How far from the grand mean? Sum squared errors, so you're basically getting the, you can imagine like it's the SSE is equal to SST minus SSG minus SSB, right? So the SSE is coming from this equation, right? So if I want to get this, then just get whatever here minus here, you would get this number. Okay. Next, I mean this formula. We care about the means, right? We just don't care about only the sum squares. We need to divide it by the sample degrees of freedom. So the mean squared total is divided by the sample minus 1. So you're correcting for degrees of freedom for the estimation of the grand mean. Now, between groups, I do have k groups, but I have to subtract 1, right, for the estimation of, again, it's the deviation from the grand mean. And as you can see it here, deviation from the grand mean, deviation from the grand mean, deviation from the grand mean. So every time I'm subtracting 1 for the computation of this grand mean. And sum squared, and then the mean squared between, right? It's the, I think there is something, there's a mistake here, okay? Okay, so just make sure you correct this. So this is supposed to be, it's wrong, sum squared G. And this is supposed to be sum squared B. Okay, so make sure that you correct this because this is a typo on the slide. Okay, so the mean square between groups is coming from the sum squared between groups. The mean square between blocks is coming from the sum squared between blocks. Okay, and these are correct. So I have H blocks minus 1 for the grand mean. I have K groups minus 1 for the grand mean, and then the mean squared error, sum squared error over its own degrees of freedom, K minus 1, H minus 1. This is very important because this is the computation of the F statistic. And as I said, I have 2 types of F statistic. Depending on what you want to test, right? If I'm concerned about the deviation between groups, like I'm moving horizontally, or I'm concerned about deviations between blocks, so I'm moving vertically. And as I showed you, the F statistic would make use of these numbers that you get here in order to compute the F statistic. So you would have in this situation 2 types of F statistic, and the rejection rule is the same, right? So you would have just to make sure that you're getting the correct degrees of freedom. Here it's H minus 1, here it's K minus 1. This is the numerator degrees of freedom for this one, numerator degrees of freedom for this one, and they share the same denominator, so this part is exactly the same. Okay. Okay, so this is like the general summary of everything. And again, this is our F statistic. This is the one that we will use in order to perform our test. Okay. What else? Yeah, this now I just want to talk about the interaction. What if you want to, like in the previous test, we're either testing groups or blocks. What if I want to do an interaction between a group and a block? Okay, so in other words, I want to test a specific variety of corn with a specific fertilizer. I don't want to have an analysis only of the variety or the varieties of corn separately from the 3 types of fertilizers. I want to have this interaction, this mix between the two. I might be able to get a certain combination that is best for the yield of corn, or has the highest yield of corn. Okay, so in order to do that, we are adding, like, you know this already, so we're just adding the part that is coming from the interaction, and the interaction is just a multiplication. So you're just multiplying the block with the block variance with the group variance, and you would get like this complicated formula. Okay, this is the total, the group, the block, interaction, error. Okay, so again, like in terms of the analysis of the test, it's exactly the same thing that you know, right? So this part is important. Now we are dividing our total variation into parts coming from variations between groups, variations between blocks, variations coming from the interaction, and another random component, which is the leftover, or we call it the error term. Okay. All right. So let me show you this, how we can do that on Stata. So when we go to Stata here, I'm sorry, I didn't mean to show you this. Oh. Okay, so I just updated the do file, and okay. So now I'm going to show you how to perform the F test, or the different types of the F test in Stata. So let's get the data set. So we are going to be using the highway quality data set. So I don't have anything to clear. So let me just go ahead and get the data. So when I get the data set, and because the names of the firms are in letters, so I just want to rename them. Okay, and we have our regression, which is regressing the different factors affecting the quality of a highway. Okay, and now we can get to our very first main F statistic. So the F statistic that you see here, right, it's actually computed from, can you see here, this is the mean square of the model, and this is the mean squared of the error. So based on the first F statistic, which I called it the model F statistic, which is the one that you get right here, you can go ahead and make sure that you get the same number. So all what you need to do is you get this number, which is the mean squared explained. You can call it, it's called here the mean squared model. So if you divide the mean squared explained or the mean squared model by the mean squared residuals, you would get this 91.06. Okay, and the 6 here stands for the 6 regressors I have. Okay, and this number is N minus k minus 1. So 952 minus 6 minus 1. Okay, so you get the 945. So this is for the overall. What about if I want to do a subset of the regression? So if I want to do a subset, we do a command which is called test PARN. Okay, so you're testing the certain parameters in the model, right? And this is called the test PARN. And how can you do that? You basically run your regression and you choose what are the variables you want to test. So let's see, I want to test whether car per miles, latitude, age of the road are important factors affecting the quality of the road. So you basically run this test, and what you get here is an F statistic. So this F statistic was computed from the restricted versus the unrestricted model. I know that you cannot see the unrestricted model here. The one that you see here is called, I'm sorry, the one that you see here is called the unrestricted model. So you can see the unrestricted model, right? What you cannot see is the restricted. The restricted model is done in the background of Stata, where they did like remove this variable, this variable, this variable, and the restricted model is a model where quality is regressed on Boras, Peters, cost PM, and that's it, and a constant term, and that's it. Okay, so this F is computed based on the restricted versus the unrestricted model, but you cannot see it, but this is the output that you get. You take this one and you go to the F table with 3 degrees of freedom for the numerator, right? Because I'm testing 3 coefficients. These are the restrictions. These are the Q number of restrictions, and n minus k minus 1. And this number is actually huge. You will not find it in the table, but you will find the very last row of the table called infinity. So that's why I'm saying whenever I have a large sample size, I can just approximate it by using the infinity row, and you will get the critical value and use it to compare with this one. And it's also easier to look at the probability. So there is a 0 probability that the null is true. There is a 0 probability that the 3 coefficients are equal to 0. So you would reject the null hypothesis and conclude that the 3 coefficients are statistically or jointly statistically significant. Okay, all right. So these are kind of straightforward. So let's see the one-way ANOVA. So in this, let me just maximize this so you can see it. So here in the one-way ANOVA, we're using the apple trees data set. And in the apple trees data set, you run an experiment. What you need to do is to vary the amount of fertilizers. And remember, this is the only factor that you are checking how it affects the growing of apple trees. So you are testing 4 treatments, right? 4 amounts of fertilizers, you can call it treatments. So we test 4 concentrations, using each concentration in 3 groves of 12 trees, and you measure the average weight of the fruit by the end of the year. Okay, so the data for this Apple dataset is already built into Stata, so I don't have to send it to you. We just need to clear so that we can load the dataset. So this is already built in its data. Okay, so you just list the observations that you have. As you can see here, I know that these are 12 trees, but two of the observations were deleted because they couldn't account for the weight for these 2 trees. So they, based on the research paper, they basically said they dropped 2 of the trees. So they ended up by having only data on 10 trees. And as you can see, this is the weight of the first, the second, right, and so on. And this is based on the different treatments, treatment 1, treatment 2, 3, and 4. Okay, next, we want to see the ANOVA weight as a function of the treatment. And when you look here, what you have is, this is the sum squared of the model, sum squared of the error, and in between here I have the sum squared of the whatever variable I have in the model. But given I have only one x, then you can see that this one and this one are the same, right? So this row and this row are exactly the same. Why? Because I only have one treatment. So whenever I'm doing like just one Way Anova and I have only one factor I'm using, then you just notice that these two are the same. So you can either look at this row or this one, doesn't matter. So what can you say here? You can use this one, right? Or you can use this one and look at the table. I always prefer to look at the p-values, much easier. And what I can see here is, if you multiply this times 100, so there is a 0.13% probability that the 4 types of treatments are the same. There is no statistical, right? So there is a very small probability that there is no statistical significant difference between the 4 treatments. Your conclusion would be, you're rejecting the null because there is a very small probability, and you're rejecting the null and you're accepting the alternative, and your conclusion would be there is a statistical significant difference in the weight of the apple trees using the 4 different treatments, right? So the 4 different treatments are not going to yield the same weight. I know we can see it here, but whether this is coming randomly or by test. So according to our test, there is a statistical significant difference between using treatment 1, 2, 3, and 4. We're not sure from this test which one is better, which one would yield the highest amount of weight, which one is preferred. We don't have this answer from this command, right? There is also a command called regress. And the regress command will give us deeper information after we run the ANOVA command. So if I'm interested in knowing which treatment is better, right? Which treatment would give me the highest weight? Which treatment would give me the lightest weight, right? The heaviest versus the lightest weight. So what you can do here is you can actually run the regress command, and as you can see here, what is the base level? Let me show you here so that you can understand. You know that I have level 1, I have level 2, I have level 3, and I have level 4. I cannot have the 4 levels together in my regression, and also I have an intercept, because I would have a multiple linearity problem. So in order to avoid, it's called, this multicollinearity or perfect multicollinearity problem is called the dummy variable trap, and we have discussed this before. So in order to avoid this, you're telling Stata to drop for you the base level, which is number 1. So base level is here. It could be like number 3, could be number 4, but it's by default, they drop the first group. So when you look here, what you can see is the base, which is treatment number 1, is dropped, and it's reflected or absorbed, its effect is absorbed here, okay? So the average of treatment 1 is 111.9 lb, okay, which is the average weight of the tree in treatment 1, and it seems to be the heaviest, right, out of the 4 treatments. Treatment number 1 would yield the heaviest trees, okay? And as you can see, these are in reference to this number. So 111.9 would drop by this number, which is minus 59 point around 17 for treatment number 2, and would only drop by 33.25 and 34. These are almost equivalent. So in other words, treatment 2 would give me the lightest fruit. Treatment 1 would give me the heaviest fruit. These two are almost equivalent, okay? So when you run ANOVA, then would give you like the F test. If you want more specifics about the results, then you would type the regress command. It is also important to notice that if you type ANOVA or ANOVA and the factors that you need, it doesn't matter, okay? So you can also type just ANOVA and then you get the same results. It doesn't matter, okay? So this result is exactly the same as this result, okay? So whatever, if you wanna be specific, I prefer to be specific and I write my set of factors, especially if I have more than two, so that I'm very specific about what I want to do. All right. The next one is the two-way ANOVA. So now we are analyzing factors, or at least two factors, right, that are affecting the dependent variable. So this one is the systolic blood pressure data set, and you're trying to test what are the factors affecting the systolic blood pressure for a group of 58 patients. And see, we have this kind of combination. We do have diseases, okay? So we have 3 diseases, and we do have also 4 different drugs. So you can imagine it like this way. I have patients, so 58 patients, trying to get the what are the factors affecting the increase in systolic blood pressure, and you are actually using 2 factors, a drug and disease. You can think of the drug as being the group, right? So I have, how many drugs we have? We have 1 to 4, so we have 4 groups, 4 drugs, but we also do have 3 blocks, which are the 3 diseases, okay? So according to that, you want to actually see the variations, how the variation, or which one is more important? Is it the variations per drug on the systolic blood pressure, or is it the variation per disease on the systolic blood pressure, or it's a specific drug for a specific type of disease that lead to a high blood pressure, okay? So you have like 3 different combinations, and I want you again to think about it in terms of how systolic blood pressure is affected by factor 1, disease, factor 2, drug treatment, factor 3, drug treatment multiplied times the disease. So again, the data set that we have here is a data set that built into Stata. So we're going to be using it. Just all what you need to do is to clear first. And okay, so let's clear and use it. List. Okay. All right, so here's what we have. Okay, so we have the drugs. Okay, and we have the list of observations. Let's summarize. So what we have is 58 observations. For the drug 2.5 is a mean, the minimum 1 to 4. Okay, so we have drug 1, drug 2, drug 3, drug 4. And then the disease, we have 3 types of disease. And then we have the systolic blood pressure. Okay. So this one is supposed to be 1 to 58. Okay. Okay, because the other one, it seems that I copied pasted from the previous one. I don't know why it was 1 to 8. It's just 1 to 58. Okay, so you're listing all the observations that you have. Let's read this one. So this is patient number 56, right? And this is the disease number 4, right? And this is drug 3, and this is the systolic blood pressure. Now, we want to tabulate. You can use the tabulate command, right? And the tabulate command is important because it would show you nice, like it's not related to the ANOVA, but still it would give us nice summary of our data set. These are the groups. So I have 3 groups and I have 4 blocks. and these are the different, right, observations I have, and you can add the total of observations here, total observation, and this is the total number of observations in this exercise. All right, so let's do the ANOVA where I'm trying to see how drugs, the different 4 drugs are affecting the systolic blood pressure. Is there any statistical significant variation in the drug that affects systolic blood pressure? Is there a statistical significant variation in the disease that affects systolic blood pressure, right? And this is what this ANOVA table would compute for us. So the table would compute for us the different F statistics along with the different p-values. And remember that you actually need to determine which one you need to look at. So remember, this one is this is the model, this is the whole model, right? But I do have an F statistic that we called it the F statistic between groups, F statistic between blocks. Does the variation, right, between groups matter? So you look at this number here, and there is a very small probability that the mean between groups is equal to 0. In other words, you reject the null hypothesis and you accept the alternative that there is a statistical significant variation between the drugs, right? Like between the drugs used, the 4 types of drugs used. So there is a statistical significant variation in the outcome. What is the outcome? Which is the systolic blood pressure using drug 1 versus 2 versus 3 versus 4. So they are not all giving me the same mean. There is a statistical significant variation in the mean, and my mean here is the systolic blood pressure using drug 1, drug 2, drug 3, or drug 4. Okay, what about the moving by disease? Actually, when you look by disease, there is a 16.26% that the null is true. So there is 16.26% probability that the null is true. What is the null? The null is telling me that if you move over the groups and you have group 1, group 2, group 3, right? So disease 1, disease 2, disease 3. There is no statistical, right, variation in the mean of systolic blood pressure, whether the patient has disease 1, whether the patient has disease 2, whether the patient has disease 3. So out of this, like this number and this number, or this result and this result, you can actually think about it this way: moving vertically based on this data set. So moving vertically matters more than moving horizontally. Actually, moving horizontally is statistically insignificant. There is no statistical significant variation in systolic blood pressure if the patient has disease 1 versus 2 versus 3. They all have almost the same mean, same mean of systolic blood pressure. However, it matters more when I move vertically. In other words, there is a statistical significant difference in the mean of systolic blood pressure if the patient uses drug 1 versus drug 2 versus drug 3 versus drug 4. Okay, so these are the 2 F's that matter for us, right? This one and this one. This one actually is about the overall of the model altogether, but really when I'm talking about the ANOVA two-way analysis, I'm talking about which one matters more: moving by drug, which is block, moving by disease, which is group. Okay. Next, what if I'm interested in knowing whether okay, so this one was like drug, how drug affects systolic blood pressure, how disease affects systolic blood pressure, holding drug constant, And again, when I analyze drug on systolic, I'm holding disease constant. Now I'm doing an interaction, the effect of both together at the same time. Does that really matter? So we need to check that, okay? So is a specific drug has an impact on systolic blood pressure given that the patient has a specific type of disease? Okay, so you would have to compute the F interaction. What about the F interaction? The F interaction is telling me that there is a 39.58, this is a huge probability, right? It's almost 40% probability that the null is true. So there is no statistical significant difference between the mean of systolic blood pressure if I'm using the interaction between drug and disease, okay? So whether you care about the effect of a specific drug on systolic blood pressure in the presence of a specific disease, it doesn't matter. So you don't have to worry about analyzing this. Your main conclusion out of those three F's is, this is what really matters, right? There is what really matters in the systolic blood pressure is the variation between patients in using the drug. There is no significant variation between patients of different diseases on the mean of systolic blood pressure. There is no statistical significant difference on the mean of systolic blood pressure between the patients given I'm analyzing drug simultaneously with disease. Okay, so that's basically the main conclusions that you would get out of this analysis of a two-way analysis of variance. Okay, all right, so I'm gonna stop here and I'm gonna ask you to do practice number 9. Practice number 9 is related to the material